Okay, here we are. Sorry, I was a bit late. For some reason, um, Zoom was not behaving properly and I had a hard time getting it started. All right, but here we are, and allow me to show my screen. Get rid of all the junk on my desktop here. Share screen, and now you should be able to see my screen, okay? And let me make sure my speakers are on, just in case somebody wants to say something. All right. I have not posted my solution. Let me do that to assignment number 12. I thought I had done that, but apparently I have not. So let me go ahead and do that. Okay, hang on. Looking at all these job descriptions for NASA. So, be sure to check this webpage because a new position has just opened for a UI UX developer. So if you're good at developing user interfaces and user experience, then this is the job for you. So take a look at that job description. But what I want to do is right now post my solution to the assignment number 12. So let me do that right now. Okay, so this is 180, and I'm now going to post the solution. I think I've mentioned before that I often teach COMPI 280, which is the web design class, and I teach all these wonderful packages for developing web applications. And so what do? When I have to maintain my web page, I go in there and edit HTML directly, and I don't use any of the packages that I teach. So, all right, so that should make the solution visible. So now it should look like this.
Now, excuse me, Professor.
Yes.
For the course you just mentioned, you use only HTML or other languages as well?
Oh, for 280 is JavaScript, and
Yes.
that is the language for the web, and so we learn about the various JavaScript packages for developing web applications: jQuery, jQuery UI, React, and so forth. So when I'm teaching that class, I'm teaching in JavaScript. I also teach in Java, C++, and Python. And so I make all kinds of mistakes in class because I get all the languages mixed up. Okay, so
one more question.
yeah.
Can we take that course as a graduate student?
COMPI 280 is a graduate class.
Perfect. Thank you so much.
I don't think I'm teaching it in the spring, but it is offered in the spring. I believe it's in the evening. I don't remember what day. When I teach it, it's in the morning. So, but I don't think I'm on the schedule to teach it this spring. But
Thanks for letting me know.
Yeah, I haven't seen my complete schedule yet. So I don't even know if I'm teaching this C++ class next spring. They haven't told me yet. Okay, let me upload the solution. Okay, so that would be 180. So you're seeing how the sausage is being made when I'm updating my website. Assignments, assignment 12, and I need to, okay, here's the solution. And I need to upload the solution, which I have on my laptop. And let's see, this is 280. Assignment 12 solution, and uploading the zip file. There it goes. And now I need to upload a new version of the class web page. And that's going up there right now. And now you should be able to see it. So let me make sure. Okay, there it is. And if you click on the solution, okay, see, file permissions. All right, I gotta fix the file permissions. Okay, you can see how much of a hassle this is sometimes, especially when I have 5 classes. But I'll manage. Okay, file permissions. I want to allow you to read. Okay, now okay. And so if everything went all right, you should be able to download it. And yes, you can. All right. Success. Okay. Only took me 5 minutes to do all that. Okay, sorry about that. I mean to do all this before class, and sometimes I get distracted and I don't. And I don't want to upload them too far in advance because you know, some of you are still working on it to the last minute. Okay, so there is a solution, and as you saw, there were a lot of different classes. So this is an example of a fairly large program that has a lot of different classes. Now in CodeCheck, there are only a few places where, well, not a few, but you didn't have to write the entire program. You had to write the guts of the various sorting algorithms. I don't know if it's worth going over my solution because actually it's a pretty straightforward implementation of the various algorithms that I gave in class. So for example, if you want to look at, I don't know, how about insertion sort? Okay, so here is an implementation of the insertion sort. So yeah, it's not terribly long. Here is shell sort. Okay, well, shell sort, there were 2 versions, the suboptimal version and the optimal version. Now the suboptimal version basically just let's see, just have, okay, each time through, it cut the interval by half, and then the optimal version used that formula to generate, yeah, here's the formula to generate the various interval sizes, okay? And so there's that solution. And so each one of them is fairly short, and it just basically implements the algorithm that I gave in class. Okay. Now I did mention that much of this code is available on the web. I mean, these are very, very, very common sorting algorithms, and there are probably dozens of implementations in different languages on the web. And I cannot prevent you from going and using any of the solutions on the web. The only thing is that you should understand what the code is doing. Don't just blindly cut and paste the code into your program. And if you do copy code from the web, then just like when you're writing a paper and you quote some author, you should have an attribution. So in your comments, say, okay, I adapted this code from such and such URL. So you should always do that. And I believe I mentioned that last week, that if you get code from the web, be sure you understand how the code works, what it's doing, and then let the grader know where you got it. Okay? All right, so I have uploaded my zip file that has my solution to it. And if you have any questions, use the discussion forum and we can discuss any issues that you might have. Okay? All right, we've been talking about data structures and the various algorithms. Okay, you certainly know all about linked lists and hash tables and vectors and you've done work with various sorting and searching algorithms and compared them. I want to discuss a very important data structure in computer science, and this is a data structure that you're going to run into a lot, and probably you're going to need it for some of your applications, and that's the tree structure. Okay, so let me define what a tree is in computer science.
Professor?
Yes?
I don't see the slides on the class webpage. Are they uploaded? Or
Oh, you don't see the slides on the class website?
no, I don't.
Okay, okay, well, maybe yet another thing I forgot to upload. Okay, hang on. Whoops, somebody needs to mute. Okay, oh, okay, no, they're not up there. Okay, let me fix that too. Okay, all right. Somebody needs to mute. I'm hearing lots of kids yelling and screaming. Okay, wow. Okay, let me fix that. That shouldn't take long. Because, okay. All right. Evidently, I somehow totally skipped over this class when I was updating everything. Okay. Fix that. Move this down to here. Of course, the recording is obsolete. Get rid of that. And today is the, hang on, let me fix coloring, right? Okay, do that here. And then today is actually not April 28th, but it's November 17th. And the slides I have to upload are today's slides. So let's put that there. And it's going to be the November 17th slides. Okay, let's see what this is going to look like. Okay. Oh, whoops. Messed up there. Okay. Lost the, there. Okay. All right, so let's see what this looks like. Okay, and all right, so let me upload that, upload the slides, and then you should be able to get them. Okay. Boy, I get several demerits today for not getting this thing all prepared ahead of time. Okay, so lectures. Oh, the slides are already up there. I just didn't update the class web page. Okay, so let's do that. And push up index. Okay, now if you refresh your browser, okay, now let's make sure the slides really do upload or download. Oh, okay, all right, now you should have the slides. Okay.
Yeah, thank you, Professor.
Okay, sorry about that. Okay, so we're talking about trees, trees. Bauman, arbor. Okay, all right, so trees, okay, tree is a collection of nodes. So just like a linked list, it's a collection of nodes. One node is known as the root node. So here's a very abstract picture of the tree. Here's the root node. And each node can contain data and pointers to other nodes, its children, okay? And so here is a very abstract picture of a tree. Here's the root node. And then it has pointers to these subtrees, which are its children. Okay. Now, in computer science, trees grow upside down. The root is up at the top, and the leaves are at the bottom. Okay, so you have to sort of picture a tree that's upside down. Okay. Now, these pointers are called edges. So these are edges. Okay. Now each child node, okay, so this root is pointing at a child node. The child node is itself possibly the root of a subtree, okay? And finally, at the very bottom, you have leaf nodes that do not have children, okay? Whoops, sorry. Each node, other than the root node, has exactly one parent node. Okay, so that's one of the key distinctions of a tree, is that every node has exactly one parent, although a node can have multiple children. Okay. All right, somebody needs to be muted, and I think I can do it myself. Okay, so somebody is not muted. And who is the culprit here? Apparently that person muted. Okay, so I don't have to do it myself. Okay, good. All right, so let's look at a picture of a tree. Okay, so let's here. So here is a picture of a tree. Okay, so A, of course, is the root of the entire tree, and you can see that A has a number of children, B, C, D, and so forth. Okay, and each child could itself be the root of a subtree. So we look at D. So D is the root of a little tree that has one child H, and here E has is the root of a subtree that has children I and J, and so forth. And at the very bottom of the tree, which would be B, C, H, P, Q, K, L, M, and N, these are the leaves of the tree. The leaves are nodes that have no children. Okay. All right, so here's an example of a tree. And of course, the root is at the top and the leaves are at the bottom. Okay. Now, I'm going to throw a bunch of terms at you related to trees. And it's not always easy to remember what all these terms mean. So you may have to keep coming back to these slides. Okay. But the path of a node from node n sub 1 to node n sub k is the sequence of nodes in the tree from n sub 1 to n sub k. Okay, so for example, what is the path from A to Q? Well, it's A, E, J, Q. Okay, and what's the path from E to J? Well, it's from E to J. Okay, so it's the path, it's the sequence of nodes from one node to the next, from one node to another node, but not necessarily the next node. Okay? All right, now the length of the path is the number of its edges. Okay, so what is the length of the path from A to Q? Well, here's the path, A, E, J, Q, and we count up the edges, and there are 3, and so that's the length of that path is 3. Okay, there's a number of edges from A to Q. Okay, so it's the number of edges, not the number of nodes. Okay, so keep that in mind. Okay, all right, and then the depth of a node, okay, is the length of the path from the root to that node. So it's basically how deep is the node from the root. Okay, so what is the depth of node J? Well, the path from the root to J is AEJ, and there are 2 edges, and so that's the length of this path is 2, and that is the depth of the node J. Okay. Well, what is the depth of the root node? Well, it's 0 because there's no path at all because it's just the root, and so therefore the depth of the root node is 0. The depth of E is 1. Okay, the depth of M is 2. Okay, so it's how far are we from the root? Okay, the length of the path from the root to that node. Okay, the height of the node is the length of the longest path from the node to a leaf node. Okay, so that's how high the node is from the leaves. Okay, remember the leaves are at the bottom. Okay, so what's the height of E? Well, the longest path to a leaf, well, in this case, P and Q, the length of the path is 2, right? And so this is the height of E is 2, okay? What's the height of the root node? Well, what's the longest path to a leaf? Well, it looks like it's A, E, J, and then to either P or Q. So the height of the root is 3, right? 1, 2, 3. 3 edges on that path. Okay. All right. So the depth of the tree, okay, is equal to the depth of its deepest node. Okay. Well, the deepest node here are P and Q, and that's also equal to the height of the tree. Okay. So remember the depth of a node is how far is it from the root. Okay. And if you find the deepest node, then in this case, P and Q are tied, that's going to be the longest path from the root to the leaf, and that is going to be equal to the height of the tree. Okay, so remember, height is how far are we above the leaves, and the root here is 3 above P and Q, and so P and Q are the depth of the deepest nodes. Well, the deepest nodes are P and Q, and so depth of the tree is the depth of the deepest node, which is equal to the height of the tree. Okay, so as I said, I'm throwing a whole bunch of terms at you, and okay, for some of you, these terms may be intuitive. For others, you just have to get used to them. Okay, all right, and we will be running into algorithms that deal with heights and depths and so forth. Okay. All right, well, how do we implement a tree? Okay, so here is a conceptual picture of a tree, but if you were to actually write code to represent a tree, how would you do it? Okay, so there are various schemes, okay? A tree node can have an arbitrary number of child nodes. So here, A has 1, 2, 3, 4, 5, 6 children, and E has 2 children, F has 3, and so forth, okay? So in general, a tree has nodes, and each node can have an arbitrary number of children. Okay. However, there's a special tree called a binary tree, where each node can have 0, 1, or 2 children. Okay, but at most 2. Okay. All right. So how should we implement a tree? Okay. So the way we would do it is that each node can have a link to its first child, okay, the leftmost child, and then each child can then have a link to its next sibling, okay, and so here is an example of how we could implement a tree node. Okay, so tree node has some data, okay, and a tree node has a pointer to its first child, right? Remember, the child itself is, of course, is the tree node. And then each tree node has a pointer to its next sibling. Okay, so it's the node to the right. Okay, that has the same parent, of course. Okay, so now what about a leaf node? Okay, a leaf node has no children. Therefore, a leaf node, the first child link would be a null pointer. Okay. All right, so here's what it would look like. So this is the conceptual view of the tree. This is how it's actually implemented. Okay, so each node, okay, let's take a look at the root, would have a pointer to its first child. Okay, and then each node will have a pointer to its next sibling. Okay, so if B, C, D, E, F, and G are all children of A, then B would point to C, C would point to D, etc. So you kind of have a linked list going across, okay? And then here's D. Well, D has 1 child, and so its first child link would point to H, okay? Here's E, its first child is I. I has a sibling, J, so it's pointing to J. J has 2 children, P and Q. So J points to the first child, and P points to his sibling, and so forth. Okay, so this is how we could implement the tree. Okay, now it's the same tree. Okay, this is what the tree conceptually is, and then this is how we actually implement it. Okay. Any questions? Okay, I know these two pictures look quite different, but this is the conceptual view of the tree, and this is a picture of how we would actually implement the tree. How we would actually write the code with first child and next sibling pointers. Okay. Now, is there an alternative implementation? Say, if I were to implement a tree, I would not do it this way. I wouldn't have all these sibling links. What I would do is have a vector, because here's tree node, here's its data, and I would have a vector of its children. okay? And so the way I would do it is that node A would have a vector, and that vector would contain nodes B, C, D, and E, and so forth. And node D would have a vector that contains H, and node E would have a vector that contains I and J. Okay? And so this, I would call this my children vector. Okay, and if it's a leaf node, then of course the children vector would be empty because a leaf node has no children. Okay. All right. So this is how I would probably implement a tree. Okay. Now there may be instances where it's advantageous to implement a tree this way. Okay, but I don't remember ever wanting to implement a tree this way. Okay, so but it's up to you. I mean, as long as you are able to say that here's a node and here are the children of the node, and you want to maintain an ordering, right? So this is not just a collection of children, but the children are ordered. You know, B is the oldest child, and C, D, and so forth. So there's an ordering implied, and of course, this linked list maintains that order. And if you're like me and you put all the nodes in a vector, well, a vector, of course, would maintain the order. Okay. All right, so there are various ways that in the C++ code we can implement a tree node, and then of course we have to be able to link up the nodes so that they become a tree. Okay. Now you notice that in each of these implementations, a node has pointers to its children. You know, whether you do it this way or you put a vector down there. Every node will have some way of getting to its children. Now, I mentioned that in a tree, every node has exactly one parent, right? And so it's possible that you might want a parent link here to point back up to the node's parent. Okay, so depending on the application, you may or may not need each node to have a pointer back up to its parent. Okay, but the way it's currently implemented, either here or with the vector, is every node knows its children, but doesn't know its parent. Okay? And so in some applications, you may want to make sure that every node has a pointer back up to its parent. Okay? All right, so how you implement the tree really depends on the application and which implementation turns out to be most effective for your application. Okay? All right, so you've seen two ways of implementing a tree. Okay? All right, well, once you have a tree, okay, what do you do with that tree? Okay, well, obviously, you want to visit the tree, and well, you want to visit the nodes of the tree, because remember, each node has some data, and presumably that data is important to your application, and so your application has to walk or traverse the tree. And what that means is that you somehow access each of the nodes, you access the nodes of the tree in order to get at the node's data. And then from that node, of course, then you can go visit or access the children of that node. Okay. So this is another term, visit. Visiting a node means you're accessing the node and then doing whatever you need to do at that node. You could be doing something with the data that's in the node, or you printing out the node, whatever. Okay? Whenever you are accessing a node of a tree, the term is that you are visiting that node. Okay. And again, this is terminology that you're going to run into. Okay. All right. Well, now how do you visit the tree, or how do you visit the nodes of the tree, and in what order? Okay. Well, presumably you start with the root. Okay. You start with the root, but then from the root you can take various paths. Okay. You can Well, let's see what these various paths are. Okay, so there is a term called pre-order tree traversal. Okay, now each of these tree traversal algorithms specify the order that you visit the nodes. Okay, and then of course, when you're at a node, you can then go visit the children of the node. Okay, and so you have to follow the links that each node has. Okay, all right. So pre-order tree traversal. Okay, you visit the node before visiting its child nodes. Okay, so that means you're visiting the node and you're doing something with the data in that node, and then you go and visit the children of the node. Okay, and this is a recursive definition, right? Because when you visit a child, okay, well, you do the same thing. You do something with that child's data, and then you go and visit that child's node's children. Okay, so it says very, very recursive. Okay, which is why we spent some time a couple of weeks ago learning about recursion, because you're going to see that a lot of these algorithms make use of recursion. Okay. All right. So pre-order says you visit a node, and then you go visit the node's children. Okay. So the pre says visiting the node before visiting the children. Okay. All right. So here's a tree, and it represents a Unix directory. So at the very top, we have star user, and inside directory star user, we have directories Mark, Alex, and Bill. Inside directory Mark, we have directories book, course, and junk, and so forth. So obviously then the leaf nodes are going to be either files or empty directories. So these are the nodes that have no children. Okay, so here is a tree that represents a Unix a directory structure. Okay, now what we want to do is print out all the names of all the nodes. Okay, but we're going to do it in pre-order. Okay, so that means we visit each node first. So here is list all, and I'm going to print the name of the node that I'm visiting, and then if it's a directory node, I'm going to then call list node or list all recursively on the children. Okay, so we visit the node, and in this case, what we do is we print the name of the name of the node, and then we recursively visit the children. Okay, this is a pre-ordered traversal, and if we look at the output, it's going to look like this, right? First thing we do when we visit a node is go ahead and do whatever operation. Okay, so we print out user, then we go and recursively visit the children. So here I am visiting Mark. First thing I do is print out Mark, and then I have to go visit Mark's children. Okay, well, the first one is book. So here we write out book, and now we visit book's children, and that causes us to print out CH1, CH2, and CH3. So here they are. Okay. Now, when we were at Mark, we had to visit the children. We first visited book, and then we go, when we're done with book, we visit course. So here we write out course, and of course, we then visit the children of course, which is just this cop, whatever, and so that gets written out here. And now we visit the children of this node, and the first one is fall. Okay, so we write out fall, we visit fall's children, and we write out SYL. Okay, when we're done with this child, we go visit the next child, that's SPR, and here's SPR, and I guess these are syllabi, and then the summer, and so forth. Now we're done with the children of well, we're done with with COP 3530, which means we're also done with the children, of course. And then we go back up and visit the remaining child of Mark, and that's Junk. So we write out Junk, okay? And Junk has no children, so then we're done with Mark, and we go back up to here, and we have to visit the next child, okay, which is Alex, and so forth. Okay, so you can see that the pattern here is that whenever we land on whenever we're visiting a node, okay, before we visit the children, we process that node, and that involves writing out the name of the node, and then we go and visit the children. So here we write out Bill, okay, and then we visit the children. Here's work, okay, there, write out work. Work has no children. Then we go and visit course, okay. Course has one child, which is this COP 3212, and then there's fall. We print out fall and then its children, and then fall again and its children, and so this is an example of a pre-order traversal, right? We process the node, and then we go and deal with the children. Okay, that's a pre-order traversal, and if we follow this traversal, we will end up visiting every node of the tree, but in a prescribed order. Okay. All right. And any questions about pre-order? Okay. Then there's post-order. Okay. Now, post-order says take care of your children first, and then take care of yourself. Okay. So when you visit a node, you're going to process the children of the node, and then when you're done with the children, you process the node itself, okay? And so you're visiting the node after visiting the children. Okay? All right, so here again is a Unix directory structure, and what we have here are, I guess, the file sizes, okay? So let's see how we actually were able to calculate all these file sizes, okay? So, all right, so we're gonna do a post-order traversal, okay? Now, this code is a little bit confusing because it looks like pre-order, but you can see that we are going through the children, calculating the size of each child, okay? And that itself is recursive, so you can see the recursiveness here. And then at the end, you can see that we're adding to total size. Now, total size starts out being the size of the file itself or the node itself, okay? And then as we're visiting the children, we are then accumulating the sizes, and then we return the total size. So I guess the visit is returning the total size, which occurs after we've visited the children, okay? Well, let's see how that works, okay? So what we want to do is figure out all the sizes here. And so, okay, we start out at the root, but then remember, we have to visit the children first. So we go down to Mark. Okay, well, Mark, we visit the children first. We go down to book, visit the children first, and we finally have these three leaf nodes with the sizes 3, 2, and 4. Okay. All right. So now we have we add up the sizes of the children, and so we have what this is 6, 9, and then book itself is 1, so that's 10. Okay, and so here the size of book is 10. Okay, all right, now we're done with book, and we're going to go down and work on this path again. Visit the children, visit the children, visit the children, and so we finally get the size of this guy is 1. Okay, and then that 1 is added to the size of directory, so now fall has to be 2, okay? And then we come and visit here. This would be 5 and 1 is 6. Okay, so SPR is 6. Okay, here's 2 and 1 is 3. So here's the 3 for sum. And then, of course, all of those sizes are added up to COP 3530, and we get 12. Okay, and then when we visit course, of course we visit the child first, so the 12 gets added to the 1, and so course now has 13. Okay, and then finally we visit junk, which is 6. Okay, and then the 3 sizes are added up to mark, which itself is 1, and we get 30. Okay, okay, so the total size of mark is 30. Okay, right? That means we're done with this child, and coming back to user, we now take care of the second child. And of course, when we get to Alex, we have to visit its children first. That gives us junk is 8. Okay, there's the 8, and we add that to Alex. We give us 9 for Alex. Okay, and we come down to do Bill. Okay, well, Bill, we have to do his first child, which is work, and work is 1. Okay, and then we do a second child, which is course. Okay, but we have to do his children first, and here we do the children first again, and you can see that we're adding up the numbers from the bottom, and then the numbers roll up to the top, and finally, when we're completely done, we'll have the total size, which apparently is 72. Okay, so this is a post-order traversal because we have to calculate the sizes of the children first, and that's done recursively, and then we add the sizes of all our children to our own size, and then that sum then is rolled up higher in the tree. Okay, so this is an example of a post-ordered tree traversal, and it's most obvious when you look at the printing here, is that we always do the children first before and then we roll up that sum to the parent, and then the sums keep rolling up till we get up to the root, and that will give us the final grand total size. Okay, so this is a post-order traversal. Okay. All right, so okay, here I was doing this slide, and my cat, who's an expert at trees, decided to take a close look at the slide. Okay. All right, so I gave you some information about trees in general, but you know, the most important trees in computer science are binary trees. So again, a binary tree can have each node of the binary tree can have 0, which means it's a leaf node, or 1 or 2 children, okay, at most 2. Okay, so here's a generic binary tree. We've got the root, and you can see it has 2 children, and then each of these subtrees are themselves binary trees. Okay, so here is an example of a binary tree. Okay, you can see that each node has 0, 1, or 2 nodes. So here, B and C are leaf nodes. They each have 0 children, and this plus sign, well, excuse me, let me see, there's a node with just 1. Okay, there isn't, I don't see a node here with just 1 child, but then you can see plus has 2 children, okay, and multiply has 2 children. Okay. All right, so this is a binary tree, and this tree represents this expression. Okay, so here we have A plus B, okay, times C. Okay, so you know that multiplication has higher priority than addition. So the B and C, B times C, have to go together, and you can see here B times C, and A is added to that. So here's A plus the B times C. Okay, and then down here we have D times E. Okay, plus F, okay? And all that is multiplied by G, so this whole subtree here is multiplied by G, okay? And then the whole thing is added together. Okay? I just got a warning that my internet connection is unstable, and this was happening earlier in the day, so I hope that we don't have a situation in the middle of the lecture that I lose the connection. It's raining, and so who knows, maybe that's causing it. Okay. All right. Now, how did we walk this tree, okay, in order to get postfix notation, okay? So here is this expression in what is known as postfix notation. And the way that works,
Oh. Is the professor disconnected?
Yeah, looks like it.
Okay, thank you.
okay, I believe I'm back. Let me share my screen again. All right, I don't know when I got dropped off. Did everybody at least see the start of slide 18? Or
Yes.
should I? Okay, all right, so my question was postfix notation. So the way that works is that you're going to do the calculation using a stack. And so here we push the values of A, B, and C onto the stack. We do a multiply, which pops off the top two values, multiplies them together, and pushes the product back onto the stack, okay? And then we do an add, which of course adds A and the product of B and C, and so forth. Okay, so I'm sure some of you have seen postfix notation. So given this tree, how do we get from the tree to postfix notation? And this is known as a post order walk. So again, we handle the children before we handle the node itself. Okay, so let's walk this tree. Okay, so we start out at the root. Okay, do the children first. That takes us down here. Do the children first. So that gives us the A. Okay. All right, now we come back up here and do the second child of the plus. Okay, that takes us to the multiply. Well, do the children first. That gives us the B. And then we do the second child, which gives us the C. Okay. Then we do the node itself, which gives us the plus. Okay. And then we move back up here, because now we've done the children of the plus. And this gives us the star, and then this gives us the plus. So that gives us A, B, C, star, plus. Okay. All right, now we're done with the left child of this root, and we have to do the right child. Okay, so the right child, okay, we land on this node, do the children, okay, do the children, do the children. So that gives us, we do the D and the E, okay. Then we do the node itself, which gives us the star. So here we got D, E star, okay. Move up here, do the children. Well, we've done the left child, now we do the right child, that gives us the F. Then do the node itself, that gives us the plus. Okay, come back up here, do the remaining child, which gives us the G. And then we do the node itself, which gives us the star. And finally, we do the root, that gives us the plus. So by doing a post-order walk, we end up with postfix notation. Okay. All right. So this is a very useful algorithm to know, is walking in a tree using a post-order walk. Okay, so we're visiting the trees, or we're visiting the nodes in this order. Okay. All right, so that's converting from the infix notation to postfix. So once we're able to represent, this is the infix notation because the operations are in between the operands. Once we have a tree that represents this expression, which is infix, then we can do a post-order walk and convert the infix to postfix. Okay. All right, if you are writing an interpreter or even a compiler, then it may be very useful to be able to convert everything to postfix. One interesting thing about postfix is that parentheses are no longer required. See, there are no parentheses here, and yet if you follow the stack operations, you will be evaluating this expression correctly. Okay, so you can see that B times C, it has higher priority over the addition, and you can see that the B and C are multiplied, and then we add the A. Okay, so postfix is a way of writing an expression without needing to deal with parentheses. Okay, all right, and that means we have to be able to build this tree first. Okay, so let's move on. Now, there is a special form of binary tree. Okay, already I showed you the general tree where a node can have any number of children, and a binary tree where a node can have 0, 1, or 2 children. And now there's a special form of a binary tree called a binary search tree. Okay. And it has certain interesting properties, okay? So if you look at a particular node of the tree, then all the values in the node's left subtree, in other words, the left child and all its descendants, okay? All the values in those nodes are less than the value of the node itself, okay? So again, we pick a particular node, and then we look at all the values in the left subtree, and all those values will indeed be less than the node, okay? And then all the values of the nodes to the right of, on the right-hand side, in the right child, will be greater than, okay? And now I suppose you can make one of them less than or equal to, or greater than or equal to. But if we assume that all the nodes are distinct in the tree, then it is strictly less than and strictly greater than. Okay. All right. So that is a binary search tree, and before I show you an example of a binary search tree, I want to talk about in-order tree traversal. So we already saw pre-order, post-order, and now in-order, okay? So the way that works, okay, you're going to recursively visit the node's left subtree. So you then go down the path of the left child, okay? And then you visit the node itself, and then you visit the node's right subtree, okay? So in other words, the node itself is visited in between visiting the left subtree and the right subtree, and that's why it's called an in-order tree traversal, okay? So this is the third common way of walking a tree, okay? And well, of course, this one is designed for binary trees because we're talking about the left child and the right child, right? A binary tree, each node has at most 2 children, okay? All right, now, if you have a binary search tree that meets these requirements about, you know, at any particular node, all the values in the left subtree are less and all the values in the right subtree are greater, okay, if you have a binary search tree, and then you do an in-order traversal of that tree, you will end up walking that tree in sorted order. Okay, so you will end up visiting the nodes of the tree in sorted order. Okay, and we'll have to take a look at an example of that. Okay, so here on the left is a binary search tree. The one on the right is not. Well, let's see why. Okay, so here is 6. Okay, all the nodes on the left-hand side are less than 6, and all the nodes on the right-hand side are greater than 6. Okay, now let's look at 2. Okay, all the nodes in the left subtree are less, and all the nodes on the right subtree are greater. Okay, let's look at 4. All the nodes in the left subtree are less, and there is not a right subtree. Okay, so this is a binary search tree. It's a binary tree, and it has that additional requirement about the values of the nodes. Okay, now this one here looks like, well, it is a binary tree, but it is not a binary search tree. And can anybody see why? Why is the tree on the right not a binary search tree? It's a binary tree, but it's not a binary search tree. Okay. What makes the tree on the right not a binary search tree? Okay.
Is it because of 7?
Yes, it's because of the 7. And why is 7 out of place? Because look at 6. Okay, well, in order for it to be a binary search tree, all the values in the left subtree have to be less. And oh dear, there's a 7. Okay, so in order to make this a binary search tree, where do we have to move the 7? Okay,
To the root?
7.
To the root?
Well,
To the left side of 8.
Okay, we can make 7 the left child of
Yeah.
Then it will be then it will be a binary search tree. Okay, all right, well, let's take a look at this tree on the left, which is a binary search tree, or a BST. If we do an in-order walk, okay, all right, so let's do an in-order walk. We start with 6. Okay, well, this is the left, this is the left, and so we write out the 1. Now we visit the parent, which is a 2, right out to 2. Okay, now visit the right, okay, recursively. Okay, we're at the 4, we got to visit the left child first, so that writes out the 3. Now we can visit the parent, okay, and that writes out the 4, okay. All right, so we're done with the left child of the root, and we then visit the root itself, which is 6, and then we visit the right child, which is 8. Okay, so then if you look at the numbers we've written out, we have indeed written them out in sorted order. Okay, so if we have a binary search tree, then this is a feature that if we do an in-order traversal, that means we visit the root, which in our case is writing out the value. Okay, we visit each node in between visiting the left and right children. Okay, so when we're at 2, we visit the left child first. That gives us a 1, and then we visit the root itself, which writes out the 2, and then we recursively visit the 4, which says, okay, visit the left child, the 3, now visit the node itself, which gives us the 4, and so forth. Okay, so if you think there's a relationship between a binary search tree and a binary search that we were doing a few weeks ago, yes, there is a very strong relationship, and I think you will start noticing it when we talk about searching a binary search tree. Okay. All right, so this is an in-order tree traversal, and of course we can talk about in order only for a binary tree, because in order says you visit the node in between visiting the left child and the right child. Okay? And if it's a binary search tree and you do an in-order traversal, then you end up visiting the roots or the nodes in their sorted order. Okay. All right, so let's do a binary search tree. Okay, and well, we can then say, well, what kind of data will we put in the tree? Okay, and that can be a parameter. So here, binary node is actually a template class. Okay, and the placeholder is called comparable. Okay, well, we'll see why we call it comparable later. And so you can see here that the data that we put into the node is of type comparable. And then you can see the pointers to the left and right children here. Okay. And so when we construct a binary node, we can maybe all we do is pass in the data, okay? Or we can pass in the data and pointers to the left and right subtree. So depending on the situation, we can use one or the other constructor. Okay? Now I'm looking at this. Okay, all right. So I just noticed that here I'm passing in the data as a constant and by reference, and I'm not doing it up here. So I'm just wondering if this is a typo or there was some reason that I did it that way. But anyway, these are the two constructors. Okay. All right, and so here, if this is the template class for the node, each node of the tree, then the tree itself is also a template class. It's called binary search tree. And you can see that okay, see here, okay, here are the constructors and the destructor. Okay. And I have an operator here for comparing trees. Okay, so I've overloaded the well, no, I'm sorry, there's an operator for making assignments of a tree. So I can assign one tree to another. Okay, here I'm getting the root of the tree. And of course, the root itself is a binary node. And binary node was a template class. So we have to then specify what the class of the data is. And here it's going to be comparable. Okay, again, it's the placeholder. And I can calculate the height of the tree. I can get the minimum value of the tree. I get the maximum value of the tree. Okay. Now the minimum and the maximum values are, of course, of type comparable. Okay, whatever it is. Okay. Remember, comparable is a placeholder. Okay. And I have a Boolean function that says whether or not the tree is empty. I have another function that says given some data, is the data contained in the tree, and that returns true or false. I can, given some data, I can insert the data into the tree. Okay. Now, when you insert data into a binary search tree, you have to make sure that after the insertion, what you have is still a binary search tree. So that means all the conditions for each node are still being met. And here I'm going to remove a node from a binary search tree. And again, what's left of the tree still has to be a binary search tree. So we'll see the algorithms for inserting and removing in just a second. Okay? All right, so what do we have here? We have a node, okay, which is a template class because we want to be able to specify when we create the node what is the data type of the data that's in the node. And you can see here that data is of type comparable. Okay, comparable is just a placeholder for the actual type. Okay, we have a couple of constructors that will construct tree nodes, and of course we can pass in the data to the constructor that we want to be put into the node. Okay, now once we have a binary node, we can then define a binary search tree. So this is the tree that will have those, that will be made up of those nodes. And you can see here that, again, this is another template class where again, we're using comparable as our placeholder for the actual type. And you can see here that, for example, get root here will return a binary node, a pointer to a binary node, which is parameterized by comparable. Okay? And when we're searching for data or inserting or removing certain data, again, the data type would be comparable. Okay. All right, and here we have some functions that will calculate the height of a tree, and then whereas these are the public insert and remove, okay, then the internal insert and remove will actually, well, let's see, what's the difference here? Here, the public versions, we're only passing in the data, and here, these protected versions, we're also passing in a pointer. Okay, so that says, okay, when you do an insert, then start the insertion operator at this particular node, and when you're doing a remove, do the removal operation starting at this particular node, because you have to search for the correct insertion point, and you have to search for the node that you're removing, and so these protected versions of insert and remove give you a pointer to a node where you're going to start that search. Okay, and then same thing with find min and find max here, whereas the public versions take no parameters at all. Okay, the protected versions do take a pointer where you want to start the search. Okay, so the implication for these public functions that do not take a starting node, you are starting at the root. Okay, but then the internal versions of the functions do have a pointer to a node where you're starting the search. Okay. All right. Well, let's see how we actually implement this binary search tree. Okay. So finding the minimum maximum values in a binary search tree is easy, because the minimum value has to be the furthest left node. It has to be the leftmost node. Okay, it's the node that is furthest to the left. Okay, and the maximum value is the node that's furthest to the right. Okay, and so there are two ways to find the minimum or the maximum. You can either do it recursively, or you can do it iteratively, and I will show you both. Okay, so remember, the minimum value in a binary search tree has to be the leftmost node, and the maximum in the binary search tree has to be the rightmost node. Okay, and if you kind of think about it, it's not hard to see why that's true. Okay. All right, so let's find the minimum value, and okay, actually, it's probably better if I show you an iterative version first. Okay, so let's do the iterative code to find the maximum value, which of course is the rightmost node. Okay, so we have a binary search tree, and we're calling find. Here's the definition of find max. Okay. Let's take a look at what find max, how we define it. First of all, what is the return value of find max? Well, it has to be a pointer to a node. And so, well, the data type of that node is a binary node parameterized by comparable, okay? And it's going to return a pointer to the node, so there's a star, and then we have to qualify find max, because find max is part of this class, is a member function of this class. So we have to qualify it. Okay? And so what is the name of the class was binary search, parameterized by comparable, and that is the qualification of find max. Okay? Now find max here, we pass it a pointer, okay, that says, okay, start looking at this particular node to find the max. Okay? All right, and then of course you can see that find max is itself a template class. Okay, so okay, this doesn't look right. I think this is definitely a typo here, because it shouldn't be template. I don't know what happened here. Okay, hang on, let me fix that. Get rid of this. Okay, I think that's what I really meant to say, is that find max is itself a template function, and so we say get to say comparable here. Okay. Now, some of you may have noticed that when we have template and then we specify the placeholder for the type, we can either use the name type name, or we can use let's see, have I used class? Yeah, or you can use class. Okay. There are two different ways of doing it, and really you should be consistent, unlike what I've done here. The placeholder class is not necessarily, or the placeholder type is not necessarily a class. So I generally use type name instead of class, but see here I'm using type name, and here I'm using class. But either one of them will work. You can either say class or type name for the placeholder type. Okay, so where we were, I was showing you find max. Okay, so all right, well, we're given a pointer that says, okay, start here, and obviously the first call to find max, we would be passing in the root of the tree, and basically we run down all the right pointers, so that at every node we go down, we follow the right path, and we go down using the pointer to the right subtree, and we keep doing that until we finally encounter the null pointer. Okay, and so we keep doing this, and then we go ahead and return the pointer. Okay, so we found the pointer to the rightmost child. Okay, and that's what we're returning. Okay, so and then now the recursive version. Okay, this is the recursive version to find the leftmost child, which is the minimum value. And so here's find min. Okay, and again we check to see if we've reached the pointer, and here if there is a value on the left hand side, we go ahead and return that node. So this is the node that is the leftmost. Okay, because we know that because its pointer is the null pointer, therefore it has to be the leftmost node, and so we go ahead and return that node. Otherwise, we call find min on the left child. Okay? And so this is a recursive way of running down the left side of the tree to get to the node that has contains the minimum value. Okay. Now, of course, the iterative way of doing it has to be the fastest. okay? So, yeah. So here we are returning the leftmost node, and here we are returning the rightmost node, okay? So this will give us the minimum and maximum values of the tree, okay? All right. Now, how about we are looking for a particular value in the binary tree, okay? Now, we want to take advantage of the fact that this is a binary search tree, and so we can do an iterative search. So that means at every node, we look at the value of the node, we look at the value that we're looking for, and depending on whether the value we're looking for is less than the value of the node, then we search the left child and go down the left side. And if the value that we're looking for is greater than the node that we're visiting, then we go down to look at the right child, okay? And so here is an iterative solution. Now, eventually what you hope is that you visit a node where its data is equal to the value you're looking for, and that's the node that you're going to return, because you have found the node that is equal to that has data that's equal to the data you're looking for, okay? All right, so then you're either going to go down the left side or you're going to go down the right side, and you keep doing this until you encounter a situation where you can't go any further, and therefore you know that the data you're looking for is not in the tree. Okay, so let's take a look at that. Okay, go back to the screen mode here. All right, so either we search the left child or the right child. Okay, all right, so here's contains, and okay, let's see. Looks like this slide. Let me fix this slide here. Size of the print is too big. Okay, there we go. So now it all fits well. Okay, so here it contains. Okay, and we're passed in a data value that we're looking for. Okay, and we're passed in a pointer to a node that we're starting with. And of course, the first time we call this, we would be passed in the pointer to the root of the tree. Hang on, my cat is about to walk on my keyboard. Okay, all right, so then if we encounter a null pointer, that means we've basically exhausted where that data item can be, and so we return false, saying that, oh no, the value we're looking for is not in the tree. If we actually find the data value, then we return true, saying that yes, indeed, we have found that the data value is in the tree. Now, if the data value is less than the data of the node that we're looking at, then we recursively call contains on the left child. Otherwise, if the data that we're looking for is greater than the data of the node that we're currently at, then we recursively call contains on the right subtree. Okay? So this is how we would recursively search a binary tree, a binary search tree. Okay? And this is taking advantage of the fact that at any node, values that are less are on the left, in the left child, and values that are greater are in the right child. Okay? So this is how we would then go down looking for a particular value. Okay, and this is what's going to look a lot like the binary search that we were using for an array or a vector that's sorted. Okay, we keep cutting in half the region that we're searching, and that's equivalent to looking at the left child or the right child. It's not necessarily equal size, but we are looking either to the left or to the right, and we keep doing this recursively until either we find the element, find the matching data, or we encounter a null pointer, in which case we know that the value we're looking for is not in the tree. Okay. Okay, this is a recursive version, and notice there's no looping involved. Okay. Now, I don't know if I gave you the, oh, okay, here is the iterative version. Okay, and so you can see, as long as we have not encountered a null pointer, we're either going to go left or we're going to go right. And so this is the iterative version of contains. Okay. Now, in general, the iterative versions are faster. Okay. But of course, the recursive versions tend to be more elegant. I mean, here, this looks very elegant that we don't need to have a loop because we're just making recursive calls, whereas the iterative version does require using a loop. Okay? But recursive calls tend to be, well, any function calls can be a bit expensive in terms of performance. So if you can get away with just using iteration, that is probably better. Okay. All right. So now you know how to search a binary tree to see if a particular data value is in the tree. Okay. All right. Now, how about inserting into a binary tree? Okay. So you have a binary tree, a binary search tree, and it follows all the rules. Okay, and you have a new value that you want to insert into the tree. Now, after insertion, what you have should still be a binary search tree, but of course with the additional value that you've added. Okay, you've created a new node and inserted that into the tree. Okay. All right. Well, first of all, you have to find where the insertion point is. Okay, so you do a search. As if you're looking for that value that you're inserting in the tree. So you do these searches, and assuming that the value is not already in the tree, eventually you're going to encounter that null link, right? Because you're searching for a value that's not already in the tree, and you're going to encounter a null link, and that is where you're supposed to insert the new item. So you're going to replace that null link with a link to the new node that you're inserting. Okay. All right. So let's see how that works. Okay. So so the new node then has to be attached to the last node that you visited as you were doing that search, right? Because you were at a node, and then from that node you either tried to go left or right, but you encountered a null link, and so you're going to replace that null link with a link to the new node, the one that you're inserting. And so the new node becomes a child of the last node that you visited in the tree. All right, let's, now I've been assuming all along that the values in the search tree, binary search tree, are unique. Okay, well, if you are going to insert a node into the tree and that value already exists, okay, you don't add another node, but you update the node that already exists. So for example, you could have a counter. Says, well, how frequently is this value supposed to be in the tree? So instead of inserting another node with the same value, you just update the existing node, maybe by incrementing this counter. Okay, or another solution is to have a linked list. Okay, so you have a linked list that is coming off of the well, let's say that you have a binary search tree and you already have a 7 in that tree, and you're going to insert another node that is also a 7. So either you update the existing node that's a 7, maybe it's a frequency counter, and you increment it, or if you really have to insert another node, then the 7 that's already in the tree is the head of a linked list of all the other nodes that have the value 7. Okay, so the other nodes are not really directly in the binary search tree, but they're linked to the 7 that's already in the tree. Okay? But to keep things simple, why don't we assume that all the values in the tree are unique? Okay. Okay, so how do we do this insertion? Okay, so here's a binary search tree on the left, and we're going to insert the 5. Okay, so we start by looking for the 5. Okay, well, of course, it's not going to be in there, but we start looking for it. Well, 5 is less than 6, so we go this way. 5 is greater than 2, so we go this way. Okay, and then 5 is greater than 4, so we try to go this way, but we encounter a null link. So this is where the 5 goes. Okay, so we replace the null link with a link to the 5, and there's the 5. And that's how we insert into a binary search tree. Okay, so after the insertion, this is still a binary search tree. That's important. Okay, so here is the example here. If we encounter a null link, then we replace that link with a pointer to the new node. Otherwise, we continue searching to the left or to the right. And if we do encounter a data that's equal to an existing node, then we update that node. Okay, so but the key thing is that as soon as we encounter a null pointer, we replace that pointer with a pointer to the new node. And that's where we do the insertion. Okay, we're inserting 5. Okay, we go left, we go right. We try to go right, but this is a null link. So we replace that null link with a pointer to the new node that we're inserting. Okay, so that's how we insert into a binary search tree. Okay. All right. And notice we are passing this pointer by reference because we are changing the value of this pointer, and we want that change to show up in the tree that we're passing in, and so we're then passing that pointer by reference, and so we have this weird syntax that we've seen earlier, that pointer is a pointer, there's a star, and it's a pointer that we're passing by reference. Okay. All right, so this is how we insert into a binary search tree. And okay, so this is the recursive calls, looking for the insertion point. And then when we encounter the null pointer, that's when we replace that null pointer with the new node that we're inserting. Okay. All right. How about removing a node from a binary search tree? Okay. Now, again, once you've removed the node, what is left should still be a binary search tree. Okay. So removing a node is trickier. Okay. But here are the steps. Okay. Now, if the node that you're removing has no children, then no problem. It's a leaf node, just remove it. Okay, so the no child case is simple. Okay, all right, so what about one child? Okay, so how about if we remove a node that has a single child? Okay, so well, let's remove okay, we're removing 3. Okay, so we're going to remove 3. Okay, well, no, sorry, we're going to remove 4. Right? Removing 3 will be easy, right? 3 has no children. We just remove it from the tree, and what's left is still a binary search tree. Okay, but what if we're removing 4? Okay, now this is a one-child case. 4 has one child, and when we remove it, okay, then the parent of 4 has to then take over the one child of the node that we're removing. So the 4 goes away, and its single child then becomes the child of the parent of the node that we're removing. So after removal, this is what the tree looks like. So this diagram is a little confusing, but the 4 is gone. Okay, so that this link has been severed, and what was the single child of 4 then becomes the is adopted by the parent of 4. Okay? So let's see, how can we say this? We're removing the 4, and the parent of 4 takes over the single child of the 4, the node that we're removing. Okay? So then the new tree will have a 3 here instead of the 4. Okay, so that's what the new tree is supposed to look like. Okay? So the no child case is the simplest. The one child case is not quite as simple, but not very complicated. It's basically take this link, this pointer, and point to the child of the node that we're removing, and then this node is gone, and its child is still in the tree. Okay. All right. Well, that's the one child case. Now, what if a node that you're removing has 2 children? Okay. Okay. Now this is the complicated one. Okay. And how do you make sure that after you remove a node that has 2 children, that what you have left is still a binary search tree? Now, the 2 children of the node have to remain in the tree, right? Just because you're removing the parent doesn't mean that its children go away. You're only removing that parent node, just as here, we remove the 4, but its single child, the 3, is still in the tree. Same thing will occur if we remove a node. Okay, for instance here, let's say we have to remove the 2. Okay, the 2 is gone, but what do we do with its children? Okay, and that's where things get a little bit complicated. Okay, so let's see how we do that. Okay, now I'm going to start with a little diversion. And here is a list. Okay, it's got a bunch of values and it's sorted. And we're going to remove the 5. Okay, and what we want to make sure is that after we remove the 5, we still have a sorted list. Okay, so how can we do this? Okay, so I'm going to show you a convoluted way of doing it, and then we're going to use this convoluted way to apply to a binary search tree. Okay, so now if the 5 is gone, what has to take its place? Well, it's going to be the 6, right? Because once the 5 is gone, then what will be in this position will be the 6. Okay, so this is what is supposed to happen afterwards. Okay, so if we remove a node, the 5, the replacement is the node that is immediately after it in the sort order. Okay, so we remove the 5. Okay, what node is immediately after the 5? Well, it has to be the 6. Okay, so well let's see how we can take advantage of that information. Okay, all right, so here's the convoluted way to remove a node. Okay, we're trying to get rid of the 5. Okay, and we look for the successor of 5, and that's the 6. Okay, so what we do is we copy over the value. Okay, so the successor node is 6. We copy over the value, and so now the 5 node is replaced, or the value of 5 in this node is replaced by 6. Okay, and so now we have what used to be 6 is now considered to be empty, and then we remove the empty node. Okay, so once again, the steps are we want to remove the 5. Okay, so we find the next node in the sort order, which happens to be the 6. So they copy over the value of 6 into the node. Okay, so now the red node becomes 6, and then the successor node is considered to be empty. Okay, and we then delete the successor node, and so now we have this. Okay, which is basically our list with the 5 removed. Okay. Now this solution does have a problem that can occur. Okay. What happens if we had a pointer to the successor node? I mean, what if there had been a pointer to the 6, and now we've removed the 6 and it's gone, and that can cause some problems later, because now that pointer to 6 is now a dangling pointer, is pointing to something that got removed. Okay, so let's ignore that problem for now and just concentrate on this convoluted way of removing a node from a list. Okay, again, we copy over the successor's value, and then we remove what used to be the successor. Okay, now in a list like this, or a vector, this is a very convoluted way of doing things, but it turns out this is the way we end up removing a node from a binary search tree. Okay, so let's take a look at this one. Okay, now when we are going to remove a node, we have to figure out what is the successor node. Okay, and so here in a list, okay, well, that's easy. It's just the next one over. Okay, but in a binary search tree, if you're going to remove a node and you want to find its successor, now remember, we're removing a node that has 2 children, right? Because the 0 child case and the 1 child case we've already taken care of. Now we're trying to remove a node that has 2 children. Okay, so if we're going to remove that node and we're going to use this convoluted process, we have to find the successor to the node that we're trying to remove. Okay, well, we know the successor has to be greater than the node that we're removing, and so it must be somewhere in the right child. Okay, so it's, somewhere in the right subtree. Okay, but where in the right subtree? Okay, well, it has to be the minimum value in the right subtree, right? And so first of all, it's a value that is greater than the node that we're trying to remove. But if it's a successor, it has to be the minimum value in the right subtree. Okay, now we know how to find minimum values. Okay, so that's a problem that we solved earlier. Okay, all right, so once we have the minimum value, then we can replace the value of the node that we're trying to remove with the data from the minimum, with the data from the successor node. Okay, and then we remove the successor node. Okay, well, let's see how that happens. Okay, so okay, and this will be a recursive deletion. Okay, okay, so once again, to delete a node of a binary search tree that has 2 children, okay, we first find the successor node, and it has to be the minimum child of the right subtree. Okay, so we get the value of that successor. Okay, we replace the value of the node that we're trying to remove with the value of the successor, and then we recursively delete the successor. Okay, well, let's see how that works. Okay, so here we are with our binary search tree. Okay, and we're going to remove the 2. Again, the 2 has 2 children. So we have to find the successor of 2, okay? Well, if it's the successor, it has to be greater than 2. And so it has to be somewhere in the right subtree, okay? Well, if it's the successor, it has to be the minimum child of the right subtree. Okay, so we look at the right subtree, the minimum child is 3, okay? So what we're gonna do then is replace the value 2 with the value 3, so now the 3 is up here, okay? And then we have to remove the successor node, okay? However, because this was a minimum value of a subtree, we know it does not have a left child. Okay, so it can have either 0 children or 1 child, and we know how to remove those, right? If the 3 had no children, we just remove the 3. And if the 3 has 1 child, then its single child then becomes the child of its parent, okay? And so the 4 then becomes the left child of the 5, and the 3 is gone, okay? So so now the new tree is going to look like this, okay? The 2 is gone, and the 3 is in its place, and the right child, well, and then we have to remove the successor node, and so the 4 is now the child of the 5. Okay, so if you sort of mentally wipe out the 3 that you see here, then the tree will now have the 3 here, and the 5 and the 4. Okay. So that's how we remove a node from a binary search tree. If it's a node that has no children, easy, we just remove it. If it's a node with 1 child, we know how to do that. And if it's a node with 2 children, we go through this slightly convoluted process and replace the value of the node we're trying to remove with the value of the successor, and we know how to find that successor, okay? And then we have to remove the successor, but because the successor is the minimum value of a subtree, it can have at most 1 child, or it may have 0 children, and we already know how to remove nodes that have 0 children or 1 child, and so this is how we remove a node from a binary search tree, and what's left should still be a binary search tree. Okay. All right. So the second node deletion, okay, is easy because that node never has a left child. And why? Well, just because it's the minimum node of the subtree, and therefore cannot have a left child. If it had a left child, this would not be the minimum node. Okay, so there we go. So now we know how to insert a node into a binary search tree and keep it as a binary search tree. And now we know how to remove a node from a binary search tree, and what is left should still be a binary search tree. Okay. All right. Well, that's quite a lot to take in, and so let's just take a quick look at the code. Okay, we're going to remove. Oops. Okay, we're going to remove a node that has a certain value in there, and so we first have to do a search to find the node, and so here I'm doing a recursive search. Okay, either we have a null pointer, in which case we couldn't find the node, so there's nothing to remove, or depending on the value, we either look in the left subtree or the right subtree until we finally find the node. Okay, and all right, so here we're going to then if this is a node with two children, so the left and the right, neither one of them is null. So this is the two children case. Okay, and so we have to find the minimum. Okay, so we're getting the data of the okay, we're replacing the node we're trying to remove. We're replacing its data with the data of the minimum node of the right subtree. That's what's going on here. And then we recursively remove the pointer, remove the node that was in the right subtree. Okay, and that's a recursive remove. Okay, but we know that that node can have either no children or one child. Okay, and we know how to do that. So down here is we're deleting a node that has no children or only one child. Okay, and so if it turns out that the node has no children, all we do is remove it. Okay, if it has a single child, then the parent of the node that we're removing will then take over that child. Okay, so it's either the node's left child or its right child. Okay, and so you can see here that the parent pointer is now going to take on the value of either the left or the right child of the node that we're removing. Okay, so down here is the case where a node has no children or has a single child. Okay, and up here we're handling the case where the node that we're removing has two children. Okay, so all right, so this is the two children case, and this is the no children or only one child case. Okay, if the node we're removing has no children, then that means that its left and right pointers must be null pointer, and so here then we're telling the parent of the node to set the pointer that was pointing to the node we're trying to remove to the null pointer, and therefore that node has been removed. Okay. All right, so this is how we remove a node from a binary search tree and ensure that what's left is still a binary search tree. Okay. All right, I know this can be a little confusing, but when you go back over and look at the code, you'll see that this is what's going on. Okay. All right, and there's actually some animations that you can go to, and the animations will show you inserting a node into a binary search tree, searching a binary search tree, and removing a node from a binary search tree. And so these animations hopefully will make it more clear exactly what's going on. Okay. And I think after all that, it's time for a break. And okay, so last semester we said we would break until 7:55. I think we're about 10 minutes behind last semester. So why don't we break until 8:05, a 15-minute break, okay?
Excuse me, Professor.
Yeah?
Is there any chance to have a diagnosis session to ask our problems before the final exam?
Oh, okay, so the final exam, so you want to have a sort of a session?
For problem solving, if possible.
Okay, well, that is possible because I was kind of leaving the very last class, which is in December, kind of open. And so we could spend some time there just kind of discussing all these data structures. Okay.
Yeah, that sounds great. Thank you. Thank you so much.
Yeah, now there is a textbook. The Malik textbook covers all this. I I would guess that very few of you actually bought that book because it's so expensive, but I am providing the slides from that book, and a lot of this material is online. Okay, and so if my very, very brief explanations are not sufficiently clear, then you can go online and see how other people have tried to explain this. Okay, but if you draw some pictures or look at some examples that have pictures, or you do these animations, the last time I looked at these animations, I thought they were very well done. And I hope, I didn't get a chance last night to check to see if they're still available, but if they are, the animations are very, very well done. And you can see step by step how new nodes are inserted into the tree and how nodes are removed from the tree. Okay, so take a look at these animations, and then once you understand what's happening, then the code will hopefully make more sense. Okay, because because of the recursion, the code is quite short, and you really have to understand how the recursion is working in order for the code to be this short. Okay, but so after all that talk about removing a node, you can see it's only about less than 24 lines of code. There's probably a little more than a dozen lines of code will actually do the remove, and that's because of the recursion that's being used. Okay, so let's take a break to 8:05, and when we come back, we'll look at yet another kind of binary search tree, and hopefully, well, I'm afraid that some of your brains are about ready to explode, and I think after the break, what I'm going to show you will definitely make your brains explode. But it's a very important topic. Okay, so I'm going to pause the recording, and we'll come back at 8:05. Okay, so I'm going mute. Okay, we're back, and let me share my screen again. When I was first going over these slides, earlier when we were talking about min and max, I saw a typo, and I fixed the typo. I've now already uploaded a new version of my slides, but this is kind of sad because min and max are such easy operations, and yet I managed to make a mess of it. Okay, so here's max again. Sorry, here's where finding the max, the maximum value in a binary search tree. It has to be the rightmost node in the tree, and so we call find max. We pass in a pointer. Okay, so of course, when we first start looking for the maximum value, this is going to be a pointer to the root of the tree. We do have to check to see if the pointer is null, because it could be an empty tree, in which case we cannot search an empty tree. But if it's not an empty tree, then we just keep going down the right side of the tree. So at every node, we then check to see, now remember, PTR is always pointing at a node of the tree. If the right link of the node is not a null pointer, that means we can still continue going down we can still chase the right links. We haven't reached the rightmost node yet. Okay, so that's why here we're going further down the right side. But as soon as we come to a node, and PTR is pointing at a node where the right link is null, that means PTR must be pointing at the rightmost node, and therefore we return PTR, and PTR is pointing at the rightmost node. Okay, so this is iterative code to find the maximum value. Now the code that I had before was correct. I've just rearranged it to make it a little bit easier to understand. Okay. Now, then I showed you the recursive version of finding the minimum value of a binary search tree. That's the leftmost node. And again, you see that first we are passing a pointer to a node. That when we first start looking for that leftmost node, we're passed in a pointer to the root of the tree, and we have to check to make sure that the tree is not empty. Okay. Otherwise, if it turns out that the pointer to the node does not have a left, okay, so that means we had to have gotten to the leftmost node, and so we return the pointer to that leftmost node. Okay. Now, if it turns out that the left pointer is not null, that means we haven't gone all the way down yet on the left-hand side, and so we do a recursive search, or we recursively call find min, starting with that left child. And so this is the recursive version of finding the minimum. Okay. And of course, there's a recursive version for finding the maximum and the iterative version for finding the minimum. If I were using, if I were writing the code to look for the minimum and the maximum, I would stick with the iterative version because it's faster and well, it's just faster and I think easier to understand what's going on. Right? Even though having this recursive call here may look kind of elegant. Okay. All right, so I hopefully I fixed min and max, which it's embarrassing that I kind of messed up initially because it's one of the easiest operations you can perform in a binary search tree. Okay, so we're back from our break, and then I'm now going to tell you about a special case of binary search tree. Now remember, binary search tree was itself a special case of a general tree. Binary search tree, all the nodes have only 0, 1, or 2 children, and then we have that condition where all the values in the left child are in the left subtree are less, and all the values in the right subtree are greater. Okay, so that makes it a binary search tree. Okay, now we want to optimize searching a binary search tree, and so we have a binary search tree, and we're given a value, and we're looking for that value, and of course, you're going to end up going down the tree following either the left child or the right child of each node, depending on whether the value that you're looking for is less than or greater than the value of the node that you're currently looking at. Okay. Now, in order for that search to go as quickly as possible, you want the tree to have, well, if the tree is very unbalanced, okay, which means that you come to a node where one side of the tree is much taller than the other side. The left subtree is much taller than the right subtree. You may end up searching longer than if the tree were balanced, so that I guess you can think of if the tree is a compact size where the left and right subtrees of a node are equal height, then if you're searching from the root, you don't have to go down as far in order to find the value you're looking for. Okay, so you want a binary search tree to be balanced. Okay, and what does that mean? It means that the difference in height for any node, the difference in height of the left subtree and the right subtree, the difference can only be at most 1 in height. Okay, and so that makes it a balanced binary search tree. And when you have that situation, then searches will go as fast as possible, in that the tree is more compact, and therefore you don't have to search as far looking for a particular value. Okay. Now, a binary search tree with a balanced condition is known as an AVL tree. Okay, and AVL trees are subclasses of a binary search tree. Okay, it has this extra condition, besides the less than and greater than condition. It now has the extra condition that the tree has to be balanced. Okay. All right, so now when we are inserting nodes into an AVL tree, or removing nodes from the AVL tree, not only do we have to make sure that what's left is a binary search tree, but it's also a balanced binary search tree. And so there's more things we have to do in order to maintain our trees. Okay. All right, so let's take a look. Okay, so in terms of trees that remain balanced, okay, I'm going to tell you about AVL trees. There's another form of balanced binary search tree called a red-black tree. And so you can do a Google search on red-black tree and see how they work. But I'm going to show you AVL tree. Okay. All right, so here is a balanced binary search tree. Okay, first of all, every node has 0, 1, or 2 children. Okay, now I'm not showing you any of the values in here, but yeah, assume that this is truly a binary search tree. Okay, but it's also balanced because at any node, okay, let's take this one right here, the height of the left subtree, which in this case is 1, and the height of the right subtree, which in this case is 2, do not differ by more than 1. Okay, so at any node that you look at, okay, if you compare the heights of the left subtree and the right subtree, either the heights are the same or they differ by 1. Okay, and so even the entire tree, okay, what's the height of the left subtree? And what's the height of the right subtree? And you can probably see that the height is the length of this path on the left side, and the height on the right side is going to be the length of this path, and the difference is 1. Okay, so this is a balanced binary search tree, also known as an AVL tree. Okay, so whoops. Okay, let me go into screen mode. All right, so okay, so here are 2 binary search trees. Okay, they both meet the greater than, less than conditions on nodes, but the one on the left is an AVL tree, but the one on the right is not. Why? Because the height of the left subtree is 1, 2, 3, and the height of the right subtree is just 1, so the difference is more than 1. So this left tree, both of these are binary search trees, but the left one is also an AVL tree. All right, so a balanced tree optimizes searches because, see here, if you're searching starting from the root, the longest path you have to search here is 1, 2, 3, and here, because this is unbalanced, okay, here is also 1, 2, 3, but if this were further unbalanced, in other words, the left-hand side is even higher, then you can see that if you end up going down the left side, if it's unbalanced, you can end up doing a longer search, okay? But if the tree is balanced, then whether you go down the left side or the right side, the search path differs by at most 1, okay? Whereas here, if you go down the right side, the path is 1, but you go down the left side, the path is 3. So this is a suboptimal search, okay? All right, so in fact, a truly unbalanced tree, all the nodes only have a left child, and so it just becomes a linked list that goes all the way down the left-hand side, and then that, of course, the searching is going to be much longer than if you had a balanced tree. Okay, so that's why we want to have balanced binary search trees to optimize the searching. Okay. All right, so if we want our tree to be balanced, okay, after we do an insertion or a deletion of a node, we have to rebalance the tree. Okay, and well, first we check to see if the tree has become unbalanced, and if so, we have to rebalance the tree in order to maintain maintain that as an AVL tree. Okay. All right, so you already know how to insert and delete from a binary search tree, and the resulting tree is still a binary search tree. Now we have an extra condition that it has to be a balanced binary search tree. So after inserting and deleting a node, not only is the tree still a binary search tree, but we're going to make sure that it's still balanced. Okay, and so if the insertion or the deletion caused the tree to become unbalanced, then we have to rebalance it. Okay. All right. So here's how we have to do this. Okay. Again, recursion is involved. Okay. We start out assuming that the tree is balanced. Okay, so if we're going to insert or delete a node, it has to be a tree that is currently balanced. Okay, and if after the insertion, okay, let's say we're inserting into the tree, okay, the tree has become unbalanced. Okay, that means that somewhere in the tree between the node that we inserted and the root, okay, so somewhere above the node that we just inserted into the tree, somewhere along that path, from the inserted node up to the root, somewhere on that path is a node that has become unbalanced. Okay, and because we assume that the tree was balanced before the insertion, the fact that that node has become unbalanced means that one of its subtrees is now has a height that's 2 greater than the other subtree. Okay, so we inserted a node into the binary search tree. The tree was balanced to begin with. After the insertion, the tree has become unbalanced. Okay, so that means some node on the path between the node that we inserted and the root, some node along that path is now unbalanced. And that means that of that unbalanced node, one of its subtrees has a height 2 greater than the other subtree, right? Because the node was balanced to begin with, and if after inserting one node, it became unbalanced, that means that one of its subtrees has a height that is 2 greater than the other subtree. Okay. All right. So we have to find that node that is unbalanced, and then do something to rebalance that node. Okay. So, all right. So let's say that we now have a node alpha that is unbalanced because of our insertion, and it's the deepest node that is unbalanced. So in other words, we found the unbalanced node that is furthest from the root. Okay, and now remember, this is a binary search tree, so it has at most 2 children. Okay, and that means that, okay, if alpha is that poor node that has become unbalanced, that means of its two children, one of them now has height that is 2 greater than the other tree. Okay, so so let us redraw these two big triangles this way. And so alpha has 2 children. Here is 2 children, and its children can each have at most 2 children. Okay. Now I've labeled these children 1, 2, 3, and 4 because if alpha became unbalanced because we had inserted a new node, then that insertion had to have happened inside one of these subtrees. Excuse me, 1, 2, 3, or 4. So we have 4 cases to consider. Okay, this poor node alpha has become unbalanced, and it became unbalanced because below alpha we had inserted a new node, and that insertion had to have happened either here, 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 or here. Okay, so I've labeled them 1, 2, 3, and 4 where the insertion could have occurred. Okay, now depending on where the insertion occurred, we have different operations to rebalance this alpha, which is unbalanced. Okay, all right, so case 1. Okay, this is called outside left left. Okay, so it's on the outside, and from the node is left left. Okay, case 2 is inside left right. Okay, so well 1 and 4 are on the outside, and 2 and 3 are on the inside. Case 2 is inside left right because to get to 2 you go left and then right. Okay, case 3 is inside right left, so right left, and case 4 is outside right right, so right right. Okay, now 1 and 4 are mirrors of each other, and 2 and 3 are mirrors of each other, so we really only have 2 problems to solve. Okay, but whatever we do in case 1, we sort of do the mirror in case 4, and whatever we do in case 3, we do the mirror in case 3. Okay. All right, so let us take a look at how we rebalance. Okay, so K2 is okay, let's see, who became unbalanced? Okay, well, it looks like K2 became unbalanced, right? Because its left subtree is this height, and the right subtree is this height, and they differ by more than 1. Okay, so we have to rebalance this portion of the tree, and well, in case 1, okay, that means we had to have added the node here. Okay, and we do a single right rotation. So this is case 1, the outside left left. Okay, we do a single right rotation around K1. So if we rotate the tree around K1, we end up with this, and now we're rebalanced. Okay, so this subtree was unbalanced. Okay, so poor K2 was the unbalanced node, and we do this single right rotation around K2's left child, and so now K2 becomes the root of the subtree, and you can see that what used to be the right child of K1 has become the left child of K2, and now we have a balanced binary search tree. So we still have the conditions that it's a binary search tree, but now also we have rebalanced the tree. So it is still an AVL tree. So this is the case 1, okay? And here it is, another view of it. Okay, so it looks like A is now unbalanced, okay? Because the height of the right is 1, and the height of the left is 3. And so we rotate around B. Okay, this is a single right rotation. Okay, And then what used to be the right child of B becomes the left child of A. Okay, and now we have rebalanced the tree. Okay. Okay. And okay, here's another example. Okay, so if we look at this, well, 8 is unbalanced because the left side has height 2 and the right child has height 0. And so we do a single right rotation around 7, and then we end up with this. And you can see that this was a binary search tree, and what we're after the rotations, it's still a binary search tree, but now it has been rebalanced. Okay, okay, that was case 1. Okay, case 1 is outside left left. Okay, and we do this single right rotation to rebalance. Okay, and of course, what's all that's going on here is that we are manipulating the pointers, right? The child pointers. And after manipulation, we end up with a tree that looks like this. Okay. All right, well, that's case 1. Okay. Case 4, of course, is the mirror of case 1. And so the insertion was here. Okay, is outside right, right. And to rebalance, we do a single left rotation, right? Before we are doing a single right rotation, now we do a single left rotation around K2, and what we end up with is this, and the left child of K2 becomes the right child of K1. Okay, and we still have a binary search tree, and we have rebalanced it, and so we still have an ABL tree. Okay. All right, and here's an example with letters so that you can see exactly what's going on. We do a single left rotation around C, so C ends up here, and the left child of C becomes the right child of A. Okay. So A was the root, and now C is the root, and the new root loses its left child and it becomes the right child of the old root. Okay, so that's what you have here too. See, the new root loses its left child and it becomes the right child of the former root. Okay, all right, and so that balances case 4. Okay, now the inside cases are a little bit more complicated, because they require 2 rotations to rebalance. So this is case 2. This is the inside left right. So inside left right, and so the insertion must have happened in here. Okay, and you can see that the tree has become unbalanced. Okay, all right, so we do a left rotation around K1. Okay, so after the left rotation, K2 is in this position. And then we do a right rotation around K2. And so K2, after the left rotation, ends up here. And after the right rotation, it ends up being the root. And now we have the tree balanced again. Okay, so, okay. Now let's take a look at an example with these examples. All right, so you can see that the inside left right has become unbalanced, okay, because we had inserted something in here, and so that unbalanced the tree. And so we do a first a left left rotation around B. So then E ends up here, and then we do a right rotation around E, and then E ends up on top here, okay? And we know how to do single rotations. So this is a single left rotation, and this is the single right rotation. We already know how to do those single rotations. It's just that now we have to do one right after the other to do a double left and then a right rotation. Okay, that was case 2. Okay, now case 3 is the inside right left, which is the mirror of case 2. And so, okay, so we have to do a right rotation around K3. Okay, that puts K2 up here. And then we do a left rotation around K2, and K2 ends up there. And now the tree is balanced again. Okay, so let's take a look at here. Okay, so we do a case 3, we do a double right-left rotation. We do a right rotation around D. So D ends up here. And then we do a left rotation and around D, and then it ends up there. Okay, so this is a right-left rotation. Okay. Okay, so this is how we rebalance the tree. Okay, after we've done an insertion or after we've done a deletion, we have to check to see if the tree is still balanced. Okay, if the tree has become unbalanced, then we find the node that has become unbalanced, and then we, depending on whether it's case 1, 2, 3, or 4, we do these single rotations if it's case 1 or 4, or double rotations if it's case 2 or 3. Okay, and so so there we go. Okay, after we've done the insertion or the deletion, we check to see if the tree has become unbalanced, and if so, we have to rebalance it. Okay. All right, so there we go. Okay. Okay. Now, since an AVL tree is just a binary search tree with this additional balance condition, we're going to make the AVL tree a subclass of a binary search tree. Okay. And so here is a class AVL tree. It's a subclass of the binary search tree. Okay. And now also you notice that because we're doing all these balancing operations, the height of the nodes becomes very important. And rather than constantly recalculating the height of nodes, why don't we go ahead and store it, okay, in the node itself. And then only if the height changes because of rebalancing do we have to then recalculate the height. But otherwise, if the height doesn't change, then we've stored it in the node. And so whenever we do want to check the height, we don't have to keep recalculating it. Okay. All right, so that's another thing we're going to do. And so the insert and remove operations. Okay, I guess I should have made this red. Boy, there are a lot of typos in these slides. Okay, so I'll make that red to point out that we're making recursive calls. Okay, so here is the insert operation. Okay, now to insert into an AVL tree, first we do a regular insert into a binary search tree. Remember, an AVL tree is a subclass of binary search. So we do the insert that we would have done with a binary search tree. And so you can see that we're calling insert, but we're qualifying it so that we're calling the insert of the parent, okay, which parent class, which of course is the binary search tree. And after we've done a regular insert, then we have to, sorry about that, we have to call rebalance to make sure that the tree is still balanced. Now maybe rebalance doesn't have to do anything because the tree has not become unbalanced, but if the tree has become unbalanced, then rebalance does all those rotation operations in order to rebalance it, okay? And the same thing after we're going to remove a node, okay? First of all, we do a regular binary search tree remove, okay? And then afterwards, we call rebalance, okay? So for an AVL tree, the insert call is overriding the AVL trees insert, and the remove call is overriding the the parent classes remove, but we're still calling the insert of the regular insert of the binary search tree followed by rebalance, and we do the same thing with remove. Okay, first we call the regular remove, and then we rebalance. Okay. All right, so that's what's going on there, and we have rebalance, and it has to check whether or not the tree has become unbalanced, and if it does, then it has to rebalance. Okay, and so here's rebalance. Okay, and we check. Okay, is the left side too high? Okay, well then it could be case 1 or case 2. Okay, and if it's case 1, then we do a single right rotation. If it's case 2, we have to do that double left right rotation, and we write out a little message saying that we did that rotation. And if it's the right side that's too high, then it could be case 4 or case 3. Okay, if it's case 4, it's a single left rotation. If it's case 3, it's that double right left rotation. And then you saw those diagrams, exactly what goes on during those rotations. And then after we've rebalanced, we have to recompute the, so node is that poor node that became unbalanced. We then have to recalculate the height of the node, because that node has moved in the tree. And so we have to recalculate its height. And so this is the one time that we recalculate the height. Okay, otherwise the height doesn't change. Okay, all right, and so assignment number 13 then is you're going to get to play with binary search trees and AVL trees. Okay, and this assignment actually comes in 2 parts. Okay, you're actually going to write 2 programs. Okay, I give you a tree printer class that will print out a binary tree, by binary search tree, so at least you know what the tree looks like after you've done these various operations. So this is how the tree gets printed, and you can see that it can handle a tree of up to 1, 2, 3, 4, 5, 6 levels, and down here at most 32 leaves if the tree is completely full. Okay, and here is what an actual tree would look like. Okay, so I give you a tree printer so that after you do insertions and deletions and rotations, you can print out your tree. Okay, and the first part of your assignment is to make sure that you can successfully insert nodes and delete nodes from both a binary search tree, which can become unbalanced, and an AVL tree, which you have to maintain balance. Okay, and in both cases, of course, you have to make sure that what you have left is still a binary search tree. So you have the less than, greater than conditions on each node, and then for an AVL tree, not only does it have to remain a binary search tree, but it also has to be balanced. Okay, so after an insertion or a deletion, you may have to rebalance the tree. Okay, all right, so part 1. Okay, first you create a regular binary search tree node by node, and the way I'm going to do that, I will give you the sequence of values to insert into the tree. Okay, so one by one, you're going to be inserting these values into the tree, and you're going to print out the tree after each insertion. Okay, and the tree can become unbalanced. Okay, because it's just a regular binary search tree. Okay. Okay, now once you've built the tree out of all the values that I give you, you will have this binary search tree, which will most likely be unbalanced. Okay, and then you will repeatedly delete the root of the tree. Okay, so you know how to delete a node from a tree, so you just keep deleting the root and until you have no tree left. Okay, so, and then again, you print out the tree after each deletion, and of course you stop deleting when the tree becomes empty. Okay, so you're constantly lopping off, deleting the root of the tree, okay? So this is what you do with a binary search tree, okay? Then you do the same thing with the same sequence of values, but you're going to create an AVL tree. So after each insertion, you may have to rebalance the tree, and you're going to print out the tree to make sure that not only is it still a binary search tree, but it's balanced, okay? Now, each time you have to do a rebalancing operation, you should print out a little message that says, okay, you inserted a node, and then you had to do a rotation at a particular node. Okay, so you just sort of say, okay, I just inserted node 10, and that caused node 21 in the tree to become unbalanced. And then in order to fix that, you did this rotation operation. Okay, and then again, once the AVL tree is built, you then repeatedly delete the root and print the tree after each deletion. And again, you'll have to potentially have to rebalance the tree. Okay, so that's part one. Okay, and then okay, so here is another example of you deleted node 77. That caused node 88 to become unbalanced, and so you did a single left rotation and a double right, double left-right rotation. So you basically print out what kind of rotation operations you have to perform in order to rebalance the tree. Okay. All right, that was part one. Okay, and I also provide a routine that will check whether or not your tree is balanced. Okay, so after you've done the insertions and deletions to an AVL tree, you call check balance, and it will tell you whether or not the tree has become unbalanced. Okay. Okay. Now, part two is you want to now compare the performance of a binary search tree versus an AVL tree. Okay, and you're going to generate a bunch of random numbers. Okay, some large number of random numbers, and you're going to insert those random numbers one at a time into a binary search tree and an AVL tree. Okay, the same random numbers, but one at a time. Okay, now here, because you're generating a large number of insertions, you're not going to print out the tree each time after each insertion. We're going to assume that from part one that you are doing the insertions properly. Okay. Now, as you're doing these insertions, you're going to make a bunch of counts. Okay, you're going to count how many times a node in the tree has been probed. And a probe is whenever you visit the node. Okay, so you using a pointer to take you to a node, and you perform any of these operations. You check to see whether or not the node's left or right link is null, and you use a left or right link to go to a child node, or you access the node's value. So any of these operations constitute a probe, and you're going to count how many probes you make. You're going to count how many comparisons you make. A comparison is whenever you compare a node's value to another value. And so, of course, a comparison is generally accompanied by a probe in order to access the node's value. So you're given a value, and you're basically searching the binary search tree or the AVL tree for that value. And so you're making a whole bunch of comparisons. And so you're going to count all these comparisons. Okay? And then you're going to, again, time all these operations to see whether an AVL tree or a binary search tree is performing better. Okay, and here you're doing all these various operations. Okay, now when you're doing the tree rotations, that's going to involve probing and comparing. Okay, so don't forget to count probes and comparisons during the tree rotations. Okay. All right. So after you have built these two trees, the binary search tree and the AVL tree, using these random values, you're going to search the tree for these random values. You're going to search the tree. It's going to generate another set of random values, and then you're going to search the BST and the AVL trees for the values, and you're going to be counting probes and comparisons and computing elapsed times. And here it doesn't matter whether or not you actually find the value, but you're still counting probes and comparisons and computing elapsed times as you're searching for these values one at a time. Okay, and then you want to choose a value of n large enough so that you can get good timings and so forth. And so what you want to do is try values of n from 10,000 to 100,000 in increments of 10,000 or something like that. If that takes too long on your machine, you can use a different value, a different range of values for n. But you want n to be large enough so that you can get some reasonable counts and timings. Okay. Now you're going to print out these tables of statistics that you're gathering, and you should use Excel or any graphing program to plot the probe counts, okay, as n increases. And if you do it for both binary search tree and AVL, then you'll be able to compare. Remember, we are concerned about how these algorithms scale. So as n scales, okay, you're going to then plot the probe counts and compare counts and elapsed times for both BST and AVL. Okay, and part one will be in CodeCheck, because and CodeCheck will make sure that your output is correct. Okay, part two has to be done outside of CodeCheck because of the large numbers of random numbers. Okay. Again, you can use code that you write yourself or code that you find on the web. Okay? Although my diagrams pretty much tell you what you have to do during these rotations. Okay? And let me show you some sample output. I know I'm running over a bit here. Sorry about that. But let me show you sample output. Okay, so this is assignment number 12. Okay, first of all, we are here. We are 180, and we're assignment 12. And here's the write-up. Okay, it should be there. Come on. And oh no, I guess assignment 12 was the one you finished. We're looking at assignment 13. Okay, so whoops. Close current tab. Let's look at assignment 13. Where is, okay. And you can see that, okay, so sample output is going to look like this as you're creating the BST node by node. And there's the checker. Now the charts and graphs are going to look like this. This is part two. Okay, so here is the values of n, okay? And here is, we're looking at the number of probes for searching. And so we see the comparisons here, okay? And then we, okay, well, actually I have a picture of all the charts. Come on, good grief, why is it? Okay, what's going on? My system is not opening the file. Oh, there it goes. Really, sometimes my computer is just being very annoying. Okay, so here is a probing for doing inserts, okay? And okay, looks like BST is blue and AVL is red. And so you can see that probing to do an insert into a regular BST is pretty constant, but oh boy, look at AVL, okay? And then for probing for searching, okay, well, here is AVL. Now, because the tree is balanced, searching should be more efficient, okay? And then because a regular AVL tree can become unbalanced, then you can see that the search number of probes goes up higher, okay? And okay, then we have probes for insert. Okay, here is compares for insert and compares for searching, okay? And then we have timings for insert and timings for search, okay? And so you can see that, well, inserting takes a lot longer because of all the rebalancing operations, but then searching takes less time because the tree is balanced, and therefore it takes less time to search the balanced tree. And I think that's all I asked for are these little graphs. And I did these using Excel, but you can use whatever graphing program. So once you get the numbers, okay, here are the probes for insert for various values of n, and for BST and AVL, here are the probes for searching, and then you can create the scatter plot of these points, and then ask for a regression curve through the points. Okay, and then you can easily see the trend of the growth as n increases. Okay. All right, that's all I have, and the write-up for assignment 13 should be up on the web, and I believe I've actually already opened the assignment in Canvas. If not, then it's something I have to do. Okay. All right, sorry I ran over a bit. Any questions? Okay. Trees are an important data structure, but as you can see, it's not a trivial thing. There's just so many different things can happen with trees, and you know, binary search trees, and then AVL trees. Okay, but it's important to know how to work these trees. All right, so that is your assignment. Now in code-check, part one is code-check. Yes.
Excuse me,
Question?
Professor. Yes, I didn't get the second part of this assignment.
Okay.
For the first time, for the first part, we should go over the code check. After that, we should use the output of part one and submit
well, no,
some graphs.
Yeah, you can use any code that you wrote for part one.
Yes.
And that will include things I provide you with CodeCheck. But part two has to be done entirely outside of CodeCheck. And yes, you can use any code that you have created for part one. Okay.
And
So
for part two, what should we submit? The code, a graph, or a combination?
okay, I do tell you what you're supposed to submit. Okay, so graphs, okay, example graphs. Okay, so what to submit is, okay, part one, of course, you submit the zip file from CodeCheck, and part two would be something that looks like this: the various statistics and the graphs. Okay, and you can do screenshots if you know you generate the graphs and they look great on your screen, but you don't know how to convert them into PDFs. Then you just provide screenshots. Okay.
Oh, excuse me, Professor. These numbers, these statistics can be the outcome of part number one of the assignment.
Well, part number one, you're doing insertion and deletions, right? And then you then make sure you know how to do insertions and deletions. And I will give you the sequence of numbers to insert. Okay. Now for part two, you're going to generate random numbers to insert, and you will then put in the counters for the probes and the comparisons. Okay, so you can take the code from part 1 and put in the counters, and then instead of inserting a sequence of numbers that I give you for part 1, in part 2, you randomly generate numbers to insert. Okay, and then you generate different numbers of numbers to insert, different numbers of random numbers. Oh, shoot, where did that go? Okay, so here we start out with 10,000 all the way up to 100,000 is the way I did it. And then for inserting these numbers or random numbers, you then, okay, here are the probes, number of probes for insertion for a BST and AVL. And here's the number of probes for searching BST and AVL. And then you get these counts and then you plot them. Okay, so you can see the trends. Okay? And then here, a number of comparisons for inserting and the comparisons for searching. And then I think the final one are the number of the amount of time it took to do those operations. Okay?
Excuse me, Professor, if I'm wrong, please correct me. For part number 2, we have to submit the randomization functions as well as the graphs.
Okay, so what is whatever I said in the write-up that hang on.
I think for part 2, you just want the Excel sheets, right?
Okay, so part 2 is what to submit. Copy of the insertion and search statistics from part 2, and the graph. So basically, what I'm showing you here is what you should be submitting for part 2. So you come up with these numbers and then generate the graphs.
Yes.
Okay?
Yeah. Thank you.
And part 1, you've already written the code to do the insertions and deletions. And so all you do in part 2 is take that same code and put in the counts of probes and comparisons.
Yes,
and then,
yes,
and
that
then
makes sense. Makes sense.
do the
Thank you so much.
timings. Yeah. Okay. All right. Any other questions? Yeah, I know this is a pretty big assignment, and so but part 1, I do give you not most, but a lot of the code in CodeCheck, and what you are basically writing for part 1 are the rebalancing operations, the various rotations. Okay. All right. Any other questions?
Professor,
Yeah.
would you please share the Zoom recording sometime before the weekend, please? Because my internet was dropping many times today. So
Yeah. Okay. Yes, I had that problem all day, and so I will try to share the recording. Okay.
Thank you.
Sometimes it takes a while for Zoom to give me the recording. Usually I get the recording and then it takes maybe another day or so before I get the audio transcript. Now if the audio transcript is not that important, then I'll post whatever Zoom gives me, but I've been trying to wait for the audio transcript, and then I post, then I do the post. Okay, but I will keep an eye on it, and if I get the audio transcript soon, I'll post it as soon as I can. Yeah.
Appreciate it.
Yeah. Okay. Yeah. I was having internet problems all day, so I don't know what's going on. I have Comcast, and they're usually pretty reliable, but who knows? Maybe the rain is doing something. Okay. Any other questions? Okay. Yes.
Excuse me, Professor, just one more question.
Okay.
The sample output should be like what you exactly are showing us.
Well,
For
it
part
won't
2.
be exactly the same, but I would think that the curves should be similar. Now, of course, these timings and the probe counts, they won't be exactly the same because you're dealing with random numbers.
Yes, I was asking about the statistics parts. Is this okay, or are we required to submit any Excel file for the statistics?
Yeah, you can set me an Excel file as long as there's something the grader can open up and see. Well, actually, what the grader will mostly be looking at are the charts, but then the charts are of these numbers. So I would say that if you do the AVL tree correctly, that your curves should be similar to mine. Okay, there are certain things that AVL always takes longer, and certain things that AVL does that is um, more efficient than a regular BST. And so at least that relationship you should have the same. And so here you can see that AVL is shooting up exponentially, whereas BST is staying pretty constant. And here they're both going up, but BST is growing faster than AVL. And then down here, you can see the relationships. Okay, so okay, and then for timings for insertion and timings for searching, again, you should be able to get the same kind of relationship. That, see, insertion can take longer and longer because it's spending a lot of time rebalancing. Okay, whereas searching, an AVL tree being balanced, search time should be less. Okay, so what this says is that if you have a situation where you're doing a lot of searching, but not a lot of insertions, you should keep that tree balanced. Okay, but if you're doing a lot of insertions, you can see that the rebalancing is very expensive. And so if you're doing a lot of insertions, but not that many searches, you should probably not bother with an AVL tree. So that's what I want you to see, the differences. I think the most important is the timings, okay? And you can see that searching an AVL tree is more efficient, but inserting into an AVL tree can be very inefficient because of all the rebalancing operations.
I have a general question.
Yeah.
So I've realized that the TA, or I don't know, yeah, TA hasn't graded like the past like 5 homework assignments.
Oh, really? Okay.
So I was wondering when we get grades for that. Yeah.
Yeah, I'm gonna have to get on her case because she promised that she would keep up with the grading, and I know she's a TA for more than one class. And okay, if necessary, I will have to start grading myself. But yeah, I will get on her case. I didn't realize she had fallen that far behind. I had been checking, but I guess I hadn't checked recently. Okay, yeah, thanks for letting me know. I will get on her case.
Okay, thanks.
Okay. Any other comments?
And is this the last assignment, or we have one more assignment after this?
It's currently the last assignment. So I think this is the last assignment, okay? Because I don't have another one lined up.
Okay.
Yeah.
Nothing with
You
graphs.
should hope that I don't get imaginative and come up with another assignment. But this I know this one's a pretty big one. Now, what remains is I haven't talked about any graph algorithms, and I don't think I'm going to come up with any graph assignments because then that's going to run right up against the end of the semester. Okay.
Oh, excuse me, Professor.
Yeah.
Now that this is the last assignment, is it possible to extend the deadline to reduce the pressure on the students if possible?
Well, we'll see how it goes. It may not be as hard as an assignment as you think, because in part 1 is mostly doing the rotation operations, because I supply a lot of the other code. And then in part 2, you take the code from part 1 and put in the counts and the timings. So it may not be as hard as you imagine, but I want you to have practice doing the insertions and deletions and the various rotations. Okay. Any other questions? Okay. All right, then, wow, we are way over. So let me sign off. Thank you for staying so long.
Oh,
And,
excuse me, Professor,
oh,
just
okay.
one last
One
comment.
last question, yes?
Yes, I have emailed you about my midterm exam. I would have, but I see you're busy, but I would appreciate if you give it a
Okay, email it again, because if I didn't answer, it probably
yes.
got buried. I get a ton of email every day. It's really hard to imagine.
Yeah, that makes sense.
So, if I don't see it, then it just disappears. Okay. All right,
Sure.
yeah, go ahead and
Yes.
send it again.
Yeah, sure. Thank you so much.
All right.
Have a great day.
Any other questions? Okay. All right. I'm going to stop sharing. Thank you for sticking around so long. Sorry about that. And I'm ending the meeting.